Hi, and welcome back to lecture number 10 of the course Design of Machine Elements and Systems in ABE. Still, this is a topic or a discussion on the load and stress analysis for machine design, particularly a continuation of the topic on the Mohr Circle. Well, this is going to be the actual application of the Mohr Circle, because previously it was established based on stress transformations. Now the Mohr Circle, developed by Christian Otto Mohr, a German engineer, is founded on uh, the use of the conic, the relationships of the stresses in a certain body. They have the conic section properties of the circle. And well, the importance of the Mohr circle is the determination of the critical stresses in a certain member or body of material, particularly the principal stresses and the maximum in plane shear stress. And we're lifting this same table from the previous lecture, primarily because this states the various formulae for solving the principal stresses and the maximum in plane stresses as a stress, based on the computed normal and shear stresses in a certain material or body. Now, it is important to take note that in this formulae, that the maximum for the maximum principal stresses, denoted by sigma 1 and sigma 2, the equivalent shear stress is 0, or at the portion where there is the maximum principal stresses, the shear stress equivalent is 0. And well, for the maximum in plane shear stress, there's a normal stress, and it's the average of the principal stresses, or sigma 1 plus sigma 2, the quantity divided by 2. These relationships, they've been very critical or important in the development of the Mohr circle. The Mohr circle, these properties will be, or relationships between the different stresses, will be much more appreciated and understood in the actual construction of a Mohr circle for a given problem. Now, how is the Mohr circle constructed? So, the conic section properties of circles, there should be a Cartesian coordinate system, and we let the x-axis be the normal stress, and the y-axis, representing the shear stress. To create now the circle, there has to be 2 points, and these 2 points will be the endpoints of the line that forms the diameter of the circle. To get the stress coordinates, the coordinates, the stresses are combined together. So you have the normal stress paired with the shear stress, and for the sigma x, or the normal stress along the x-axis, the negative value of the shear stress is paired, and the normal stress along the y-axis, the positive value of the shear stress, is paired with it. And afterwards, the line from the 2 points can now be constructed. That becomes the diameter of the Mohr circle, and the Mohr circle now will be used to solve for the principal stresses and the maximum in plane shear stress. Forgoing the it simplifies the formulae that is shown in this table. So without using this formulae, it's now very easy to transform the stresses, okay, or to find the stresses for combined loadings, particularly um, those engineering problems with normal and shear stresses combined. Okay, and we know that in the normal stresses we have the compression forces and tension forces, and for shear there's the torsional stress. It's now important to take a look at this problem. Okay, same problem from the previous exercise where you have an aerator that has a propeller, okay, and that propeller experiencing a drag force of 120 kilonewtons. That propeller is being driven by a drive shaft that's powered at 2,500 kilowatts and rotating at 1,000 RPM, or revolutions per minute. The shaft radius of the shaft radius holding the propeller is 100 millimeters in diameter. Sorry, in radius. Okay, and from the previous exercise, okay, from the previous lecture, the exercise from the previous lecture, it has been known that the normal stress, okay, these are the stresses in the surface of the shaft. Okay, the normal stress is negative 3.82 megapascals, while that's the shear stress. Sorry, this is going to be the shear stress. The shear stress along the surface of the shaft is 15.22 megapascals. Now, with just this two known stresses, or yes, stresses known on the surfaces of the shaft, the principal stresses can now be determined. Okay, using the Morse circle. Okay, so this is going to be along the x. Okay, so this is going to be along the x, and this is going to be along the xy surface. So we are trying to find the maximum in plane shear stress and the principal stresses. These have been already determined, and we'll be able to verify, okay, these values using the Morse circle. Our sigma 1, okay, is 13.43. Okay, and our sigma 2 is 17.25, and our shear max is 15.34. Let's move over to our drawing software so that you can plot this Mohr circle. All right, so we have here the representative Cartesian coordinates along the x and the y. Again, we have our normal stress along this line, okay, and the shear stress along the y-axis. So what we have to do is simply take or find the points, negative 3.82 and 15.22, and on the opposite side we have 0, which is our sigma y, and the negative 15.22. Okay, so how do we do that? We have now our coordinate systems. We just have to find those points, okay, the pair of the normal and the shear stresses. Let's try to do that. Okay. offset by, okay, we have to offset this by 3.82 to the left because it's negative, and we have to offset the x-axis along the y, two i's, okay, up and down by a certain value, and that would be the value of the shear stress 15.22. So up and down. Okay, so the points, okay, the points that we are trying to find are actually already identified. So this is the first point, okay, and this is the second point. Okay, we just have to connect them to get the value for our principal and principal and maximum in-plane shear stresses. We have now connected to 2 points, and we can create the circle because we have now identified the axis of that circle and also the diameter. Okay, so that would be the end of the circle. Okay, now this is now the Mohr circle that we will be manipulating to find the principal stresses. And primarily, okay, our first principal stress, okay, that we will be able to identify is this one. Okay, we have here along this line. Okay, our principal stresses are along the x-axis. So we just have to measure this first line, and the other one is going to be along this direction. And we have our maximum in-plane shear stress along this line. Just have to find the point coincident to the circle, okay, where this vertical line will traverse the circle. So let's try to do that and simply measure this distances from the 0, 0 coordinates of the Cartesian coordinate plane, and we will be able to identify now the stresses that have to be identified. Okay, so let's do so, and we begin by creating the, we just first have to measure this first principal stress and the other one. Okay, this is going to be negative because it's along or directed to the left of the Cartesian coordinate system. And then we create the vertical line. Okay, it's going to be vertical, and it has to pass through the axis. And we have now our maximum shear stress identified by the coordinate of the maximum shear stress and the average of the principal stresses. Okay, so we just have now to measure this value to get the to quantify our maximum shear stress, which is okay consistent with our solutions. Okay, it's 15.34 megapascals, while our first principal stress is 13.43, and the other other principal stress is negative 17.25. So this simplifies this simplifies the solution, and without using the equations, the formulae identified in the previous discussion, the principal stresses and the maximum in plane shear stress can be identified. Take note that as with the principal stresses, since they are along the x-axis, the maximum or the shear stress equivalent or the accompanying shear stresses are 0, while for the maximum shear stress, the equivalent normal stress or the accompanying normal stress during or within that direction, orientation in the body, it is the average of the principal stresses. So 17.294 plus 13.429443, okay, and that's going to be what? It's going to be this value, okay, it's negative 1.91. Okay, so that's the simplification of the solution, okay, for stress transformations. Now the Mohr circle is very much relevant as well um, in the combined loads. Okay, combined loads. Okay, when a body is experiencing combined stresses from, okay, the normal stress, okay, and you have also there's torsion, okay, or even shear, okay. So combined stresses, okay, actually refers to axial load, okay, torsion and bending loads combining together, okay, while acting at the same time on a body. And stress transformation is used to simplify this analysis. And the Mohr circle comes in handy, okay, to simplify the stress transformation process or analysis. Uh, in some cases, okay, since it could be a very difficult solution to do the Morse circle for 3D bodies, okay, finite element analysis is an alternative option. Okay. To solve for the combined stresses, okay, or the principal stresses in the maximum in-plane shear stress using stress transformation analysis, okay, for bodies. Okay, it is first important to determine or compute for the stresses of at the critical points where the high stresses are likely. But since there's uncertainty of location, it's important to test several points in a body. And once the critical points are identified, it's important to draw the Mohr circle and eventually solve for the principal stresses and the maximum in-plane shear stress. Now, this technique, okay, to simplify the stress transformation using the Mohr circle is a very handy tool in solving for the uh, principal stresses in, or the stresses that are of critical importance in machine design. Okay, because the bodies in machines are constantly in moving. Okay, so there's velocity, there's angular velocity, or there could be even angular acceleration. Now, the consideration of the possible principal stresses and, okay, maximum in-plane shear stress values, okay, is very important because those are unseen to the naked eye. Okay, so they're happening within the body. Okay, they're not just simply just happening on the surface. Okay, because on the surface you have if they were um, uh, equilibrium bodies or members in equilibrium, so they're not moving, then or well, statics, okay, not in equilibrium, because there could be a body, there's a body that is moving that is in equilibrium. Okay, I'm sorry for that. So you have your bodies in static equilibrium. So this principal stresses and maximum in-plane shear stresses could be um, of less importance. But in bodies that are moving, okay, particularly in machines or machinery, these are very critical. Okay, next a discussion, okay, in stress analysis is on stress concentration, and these are portions of a body or a member wherein there are discontinuities or irregularities in the dimensions, particularly in the area of consideration. Okay, the area where the force is applied to, or um, the stress, okay, that is experiencing the, or that the area that's experiencing the stress, and eventually deforming to lead to the strain in the body. Now, theoretical and geometric stress constraint factors identified as KT or K sub TS, okay, are used, okay, to relate the actual maximum stress to the nominal stress at a certain discontinuity or irregularity. And these values vary for different geometries and been determined experimentally. So this could be, okay, best um, explained using an example as shown. Okay, this is a problem, okay, where a thick bar that is actually loaded and at an end is connected to another end, okay, fixed, okay, and the material is made, or the bar is made of a material that is high strength but low ductility. Now, if it can be, it is shown that the material has, okay, a hole, okay, with which there could be something that could be placed in there, okay, probably a rope or another metal, okay. Now, it is asked, okay, what would cause the failure of this, or where is the failure, okay, probably happening, okay? Is it in the hole? What if its hole is 4 millimeters in diameter, or if the hole is 8 millimeters in diameter, and another is if it has or if it will happen in the fillet portion of this this bar, okay? So let's try to annotate this one, okay? So there is the hole, so this could be 4 millimeter in size or 8 millimeter. Now, which one would cause the cracking or the failure of this bar? Now, also there's a fillet here, okay, that's been identified as 1 millimeter in diameter, in radius. So to solve for this problem, okay, it is important to take note of the the axial load, okay, the axial load, okay. To solve for the axial load, or the stress along the axis, okay, it's just the force over the area, and the area is going to be what? The width minus the diameter, okay, over the thickness. So there's a table that's being used, okay. Again, this shows the relationship of the stress concentration factor, the case of T, to the relationship of the diameter, okay, or the diameter to the width, okay, the thickness of the bar. So if, okay, to solve for the W over D, or the D over the W, okay, we can simply identify the K sub T by plotting them, or correlating them via this diagram, okay. This is from Shigley's Mechanical Engineering Design, okay, lifted from the book under fair use policy. Okay, so let's try to solve for the problem, okay. And we are trying to find for the stress in the hole, okay, the hole, okay, for the 4 millimeter hole. Now the stress is simply a force over area, and it's going to be the force over width times distance times the thickness. Okay. I think there's a problem with the formula a while ago. Anyway, please just check. So it's 10,000 newtons over 40 minus 4 times 2, and it's going to be m squared now. Okay, I'm simplifying. This is going to be 139 megapascals. Okay. Now the sigma max, okay, is going to become, or can be determined by multiplying the k sub t with the determined value of sigma. Okay, sigma o. Okay, and it's going to be okay at dw. Okay, we have to find first the at d over w equals 4 over 40, which is 0.1. Okay, our k sub t is what? It's going to be what? Sorry, it's going to be 0.269. Okay, 269. Okay, so k sub t is 2.69. It's unitless since it's a factor, and the sigma max is going to be, okay, 2.69 times 139 megapascals. It's going to be 374 megapascals. Okay, solving for B. Okay, so this is same procedure for the 8mm hole. Okay, using the same diagram. So this is 10,000, okay, times 10. Oh no, sorry, it's kilonewtons. Newtons. Newtons, okay, divided by, okay, 40 minus 8 and 1 times 2 is going to arrive at the value of 156 megapascals. Now at T over W equals 8 over 40, there's going to be 0.2. Now the KT is going to be 0.2. It's going to be 0.25 or 2.5, sorry. It's 2.5. And so sigma max is going to be 2.5 times 156 megapascals, and it's going to be 390 megapascals. What does that mean? So that the values for the 8mm hole at 390 megapascals mean that it would be of a greater value with the 4mm hole and would significantly be the cause of a failure than the smaller hole. Let's find the cause or the failure tendency for the fillet portion. Okay, so we have C portion, which is for the fillet, and the fillet will have the same formula, okay, F over A, which is 10,000 newtons over 34 times 2. Okay, we have already subtracted um, the the um, the fillet. Okay, so it's identified that it's 34 millimeters. Okay, oh sorry, it's millimeters. Why am I using this? So it's in millimeters. But anyway, it's not important. We just have to find the relationships. Okay, so this is probably not millimeter squared. Okay, since we have to divide this. Okay, it's going to become 0.004. Okay? It's going to be even bigger. Okay, so this would eventually lead to 147. Okay, and we'll be using a different table from the table presented a while ago. Please refer to table A-15-5 of the 2020 version of Shigley's Mechanical Engineering Design, okay, 2020. Okay. This is in the appendix portion. So in that table, okay, it's important to determine the this value, the d over d, and it's going to be 40 over 34, which is 1.18. Okay, and another parameter is the radius, okay, of the fillet over the diameter, which is 0.026. And using that table, okay, it is determined that the KT is 2.5. Now, sigma max, okay, is going to be the KT times sigma sub 0, which is simply 2.5 times 147 megapascals. Apologies for that. Okay, it's 147 megapascals, and it's going to have a value of 368 megapascals. Again, please check through the values. Okay, this has to be This has to be 0.4. Okay, millimeters, 0.04. So this will be 0.036. Okay, times the hole. Okay, the thickness, that is 2 millimeters, so 0.002, and just increased by the probably 2 gigapascals. Okay, so it's going to be gigapascals already. This is in mega. So divided by 0.004. Okay, will 0.04, it will, and divided by 0.002 will give values that are much bigger. Let's try to solve that. Okay, we just have to correct the values for the suffix of mega. Okay. 10,000 kilonewtons, or 10 kilonewtons divided by 0.036 divided by 0.002. Okay, yes, it's indeed. Oh, it's megapascals. It's already correct. So this is correct. Okay, so this is in meters. Okay, so this is still correct. So the values are correct actually. So based on these values, okay, it can be inferred that, or concluded that, the 8 millimeter hole will have the greater tendency to cause the failure of this design, okay, or the structure. The 4 millimeter hole is going to come in second, while the the fillet is gonna cause it blast. Now, the next topics, okay, will be focusing on the failure of designs, okay, due to loading. And this is going to be the end of the first period, okay, where the stresses have already been incorporated to movement, okay, the kinematics. Thank you for listening, and I'll see you in the next lecture.